Chapter 8 basically defines the atom and how atoms emit light. We'll talk about this in chapter 8. Two sections. First section talks about the basics. Second section will talk about the atomic energy levels and models of that. And also, when I was talking about diffraction grating, I told you that diffraction grating is used to understand which component colors exist in the light coming from space, from stars. By studying these colors, these wavelengths, we can understand which material, which substance, or which element exists in that star. Because radiation coming from an object depends on two things. One of them is its temperature. Second one is its chemical structure. What kind of chemical structure this substance has. So all hot objects with a temperature emits electromagnetic radiation. Electromagnetic radiation. When we talk about electromagnetic radiation, all these parts are included. What are they? Starting from radio waves, which are used in communication of the radios, communication, television communication. Then microwaves used generally for cell phone communication. Also, you have most probably at home microwave oven. Maybe you know about that. Infrared for remote control devices, all are infrared radiation. Visible part, what we see, which is very small portion of these electromagnetic waves. With 1% or less than that we can see, but the rest we cannot. Yeah, and these are invisible. Radio waves, microwaves, infrared, not visible to our eyes. Only this visible part, a small portion of this, the electromagnetic radiation is visible to us. After that, ultraviolet stars. Ultraviolet has coming from sun mostly. It's also vital for vitamin D synthesis in the human body. And of course, high energy compared to the others. But X-rays are much higher in energy compared to the previous one. X-rays are used generally for taking the pictures of the human body if there's some broken arm or something like this, so you can see them very easily. But because they have very big energy, you shouldn't use it so frequently. Gamma rays are the electromagnetic waves with the highest energy. They appear as a result of some nuclear reactions, gamma rays. So this is called electromagnetic spectrum. Spectrum means range of something. So we are putting this electromagnetic radiation in terms of their energy. From smallest energy to the highest energy, this is how we put them in order. And also, you will learn later, but you can predict frequency and energy of a wave is directly proportional. And as frequency increases, energy of the wave also increases. Then you can say that radio waves have smallest frequency. Microwave is the smaller. So infrared is a little longer. Visible, and then which one has this highest frequency? Which is gamma. And from left to right, frequency increases and energy also increases. But wavelength is opposite. Wavelength is opposite of the frequency. So longest wavelength, radio waves. Shortest wavelength, gamma rays. As I said, property of this radiation emitted by a substance depends on two things. One of them is how hot the substance is. And the second one is chemical property of this substance, what kind of element it is. And as temperature of the object increases, or let me say, at low temperatures, radiation of the wavelength are mainly infrared region. Infrared radiation. For example, 36.5 is the human body's temperature. So this temperature corresponds to an infrared radiation. Not visible to our eyes, but visible for some machines, especially night vision cameras. They are using night vision cameras, for example, in border control. If somebody is walking at night, so you can see them by detecting the radiation coming from their bodies. I think most probably mosquitoes are also using that because they like hot bodies. Some people are very special for that. Some animals can detect this ultraviolet infrared radiation coming from the objects. So at low temperatures, radiation's wavelengths are mainly infrared, not visible, and a very low radiation, so they cannot be seen by human eye. But as temperature increases, this infrared radiation enters to visible region. You start seeing it. So as temperature of the object increases, the wavelength is in the visible region of the electromagnetic spectrum. It's a good example. This is a good example. Your book is explained how iron, when you melt iron and increase the temperature, how its color shifts. Molten metal is generally glow, initially, yellow glow. But when the temperature increases, it changes to white glow. And when you increase temperature much more, it changes to bluish. If it's this change from yellow to blue, you know that, shorter wavelength, yellow, longer wavelength. Yani, as temperature of the substance increases, it changes from longer wavelength to shorter wavelength. And electromagnetic spectrum, yani radiation from these substances, consists of continuous distribution of wavelength. Continuous distribution. What does continuous distribution mean? There is no space between them. And we don't say that, okay, here radio waves ends, there is a space, then starts microwaves. Microwave ends and space and starts, no, there is no space between them. So it's continuous. In this chapter, we are going to learn two new terms. One of them is continuous, the other one is discrete. Discrete is just like steps. So when you are walking, you push your left foot on one step, so next foot left on other steps. So then you are stepping up. You are moving from ground to the second floor by this way, by steps. In fact, this is discrete. Your right foot is on a level, then you are taking your left foot on another level. But inclined plane is continuous. So inclined plane represents a continuous rise, but steps are representing a discrete rise. So these two terms will be very important in this section chapter. We are going to learn about right time. So electromagnetic radiation is continuous spectrum. And there is no space between any interval. Normally we name them. There is, as I said, radio waves. Where radio wave starts, where it ends. Where microwave starts, where it ends. There's no such very strict things. Just naming business. Okay. So infrared is starting from there to there. So we gave them those numbers.
You don't have a slide.
No, there is no certain intervals. On average, they are given some values for them. Okay. As I said, most objects emit radiation if they are hot. But to emit hot, they should first get the energy. And without getting energy, how can you start emitting them? Most objects absorb some of the incoming light and reflects the rest. For example, this is dark, huh? This is white, this is blue, that is blue, this is another color. How can we see the colors? By the reflection of light from those objects. Light is coming, striking the surface of the object. Some are absorbed by the object, but some are reflected. This reflected rays makes you to see the object, what color it is. When the object is absorbing the light energy, in fact it's energy, so what do you expect? Heat must be increased. Especially you can be aware of this in the summer, when you put something across the sunlight, so it becomes hot, especially your body of your car or something around this, you can observe it. If an object, if a system absorbs all incoming radiation, it's called blackbody. If an object absorbs all incoming radiation, it's called blackbody. In fact, no object in normal life can do that. Even the cloud is black. A black cloud is not blackbody. Even there is a reflection, so you see it. You can see that. You can see that black. Black objects, of course, absorbs more than Why? Because in summer you don't wear black, huh? You wear white. Why? Because you want less absorption, more reflection to feel cool. But I mean, in the cool means not that way, okay? So, but in winter you should wear dark black compared to white because you want cloth to absorb more radiation, to heat up your body. Because there's no such a strong sun in this winter. But Blackbody is theoretically an object which absorbs all incoming radiation. But physicists find a way. You find always a way. Because this is the Blackbody. By the time Blackbody, it's a perfect observer. Yeah, it takes all the radiation. But later it starts to give it out. Yeah, it's a perfect observer. At the same time, perfect emitter. Yani, which is called radiate, a Blackbody. Physicists made a Blackbody such a way that, you see this picture? This is a hollow object with a small opening. So when light enters inside this cavity, it strikes the inner wall of this hollow object, then reflects from and then hits other surface, reflects again, reflects again, reflects. After reflection, each reflection, energy of this light is given to this body. Finally, after several reflections, all energy of this light is absorbed by this hollow object. Yani, there is no reflection. And this light couldn't escape. So this is a model of a Blackbody in physics. You are going to use a hollow object. You are going to open very small openings so that light cannot escape. So when light enters, they will collide with this inner surface. After each collision, they will give some of the energies at the end. All energy of the light will be given to the object. So a hollow object with a small opening is an example of a Blackbody. As light continues to enter from the opening, observed after many reflection in this cavity, so then we know that the hollow object starts heating up. Of course, every heated object starts to radiate energy. So as energy starts to be radiated in the form of electromagnetic waves, see that? So from inner surface you are hitting this object, but from outer surface it's starting to radiate this energy. This is what a Blackbody is. It's a perfect observer from inner surface, and it's a perfect radiator from outer surface. So why this Blackbody is so important? Because many experiments about the thermodynamics is done by this way in physics. So how does energy radiated by this Blackbody and wavelength of the light changes was for a long time. But then classical physics said something about this energy radiated by this Blackbody and what wavelength of the light is emitted. So first I am going to talk about classical models explanation about this. Classical theory of the physics predicted that as Blackbody is heated up, color shifts from red to violet. This is normally what we expected and what we observed. This can be easily observed because when you have heat up an iron, you observe that it shifts from red, yellow to blue, which is from longer wavelength to shorter wavelength. Wavelength decreases and approaches to zero if you continue heating a Blackbody. What about the energy emitted, which is the intensity of the light coming from this Blackbody? Of course, from outer surface, there must be some emission, right? Intensity of the radiation from the outer surface increases and goes to infinity. Classical model says this. And when you continuously heat up Blackbody, so then you are going to increase the emitted radiation. So if we represent these two results by a graph, this is going to be the graph. As you see, as Blackbody is heated, wavelength decreases and goes to zero. But by the time intensity of the light increases and goes to infinity. And area under this curve will give us the power given out by this black body. And as you see, this area is small when the wavelength is longer, yani less powerful radiation. But as wavelength gets smaller and smaller, what happens to the area? Area increases, so then radiation becomes more powerful. So the power of the radiation closer to the ultraviolet end must be greater than the power of the radiation closer to the infrared region, because we know that longer region is infrared. Longer wavelength is infrared, but shorter wavelength is what? Ultraviolet.
So more energy.
Yeah, when classical model says that as radiation's wavelength approaches the ultraviolet, so intensity also must increase. As intensity increases, of course, power will increase as well.
Power of emission.
Yeah, power of the radiation increases as well. But later in 19th, an experiment is done with the Blackbody. But result was not completely like this. However, experimental data of the Blackbody was contrary to classical model. How? This is classical model. As you blue curve represents classical model. So it says that when you heat up an object, the curve starts from 0 and goes to infinity. But experimental data observed that until some middle wavelength, this is correct. Yani this red is representing experimental data. Until here, both classical model and experimental data is coincidence, and they are agreed. There's an agreement between them. But from this point on, something happens in the opposite. Classical model says that intensity must go to infinity and the power must increase. But experimental data said that this is opposite. From this wavelength on, intensity starts to decrease and goes to 0. So this is a big problem. According to classical model, such a radical change cannot happen in the nature. And if something is increasing, it must continue increasing. Why? One thing is increasing, suddenly it starts to decrease. This is a new thing. This was a shock. That's why they named this event as a catastrophe. Ultraviolet catastrophe. Catastrophe, you know what does it mean? Disaster. They think they named this contradiction as a disaster. Because all the predictions until that time was destroyed. Prediction. This is a catastrophe. Her name is ultraviolet catastrophe because this happens in which side of the electromagnetic spectrum? Ultraviolet side. Right side is infrared side, close to infrared. Left is close to ultraviolet. For that reason, this contradiction between the prediction and experimental data is named as ultraviolet catastrophe. So, at wavelength smaller than this intermediate wavelength. Which was intermediate wavelength? This one, as you see. In here, we got maximum intensity at this wavelength. Maximum light intensity of electromagnetic waves. But after this wavelength, there is a disagreement between the classical theory and experimental data. This contradiction is named as ultraviolet catastrophe. This is the definition in this exam question. Because it happens where? In the ultraviolet side of the spectrum. Because left side is ultraviolet. Right side is infrared. So now this is the definition of the ultraviolet catastrophe in your book. Let's word by word, let's get this definition. The failed prediction of classical physics. Yes, classical physics predicted that radiation must go to, but in sense must go to infinity. This failed. This prediction has failed. Failed prediction of classical physics that the energy radiated by a black body, extremely short wavelength, what does it mean? Ultraviolet, should be large, and total energy must go to infinity. But this failed. This prediction has failed by experimental data. That's why this event is known as ultraviolet catastrophe. Okay? We have to know this definition. They give this definition to you, and you know they are giving definition and asking you what is this. This is how black body curve changes depending on the temperature. We said that area under this curve is defining the power of the radiation. Area under this curve, when I say area, I am talking about this. Look at that. Area under this curve is the largest, correct? What does it mean? At 700 Kelvin, power of the radiation is the most powerful radiation. But as temperature of the black body decreases from 7,000 to 6,000, area under the curve becomes smaller. Yani power of the radiation decreases. 5,000 Kelvin, much smaller. 4,000 Kelvin, much more smaller. Yani as temperature decreases, power of the radiation decreases, or vice versa. As temperature of the black body increases, power of the radiation increases. This is what we saw in our daily life. If you heat an object, of course, it starts emitting more power. One more thing also changes. Look at now. At 7,000 Kelvin, when the surface of the black body is 7,000 Kelvin, peak of this curve is at what color? Violet. Violet color. 6,000? Blue. 5,000? Yellow. And as temperature decreases, color shifts from violet to finally red. Yani this is what we in fact expected. Classical physics also said the same thing, but not on this curve, not on this experimental data. This experimental data also explains that why there's a color shift as temperature increases. So smallest temperature, 4,000 Kelvin, has a red color. 5,000 Kelvin, yellow, it changes to yellow, from red to yellow. 6,000, it is blue. 7,000, the color of this radiation changes to violet. So, as temperature of the black body increases, the peak of the distribution shifts to shorter wavelength, from red to violet. Because red is a longer wavelength, violet is a shorter wavelength. It changes from longer wavelength to shorter wavelength. Shifts from red to violet, one of them. Also, the total power emitted by the black body also increases with temperature, because this area under this curve is the largest. That's why power is the greatest. Okay, there is a huge contradiction between the classical prediction and the experimental data. Who is going to fix this? I cannot, because I was.
You weren't born.
I weren't born. Somebody must fix this or explain this contradiction. But many scientists used classical physics to try to explain the experimental data of the black body radiation, but they all failed. Why? Because classical itself is the problem. Classical physics is the problem. That's why you cannot explain something by a problem, something which is sufficient. That's why none of them could explain that by using the principles of the classical physics. One person, whose name is Max Planck, German physicist. Max Planck proposed a new model, which means if you need something very extraordinary, don't try to fix it by usual ordinary things. It needs an extraordinary approach. What Max Planck does this. So now shortly I will explain what is the similar between classical theories and Max Planck's theory, And what is different between these two? Classical theory and Max Planck's theory are similar or almost the same in two statements. First and second statements are the same. Difference is in here. I put here a cross. What they say is this. A black body radiation was produced by submicroscopic electric oscillators. On the body of this black body, this cavity, this, what we said, that object, in fact we don't see, but there are some electrical objects which are vibrating. Oscillation, you know oscillation means? Vibration. Yeah, they're vibrating. But every oscillator vibrates a specific frequency. Each of them. Yeah, a black body radiation was produced by submicroscopic electric oscillator. They are vibrating and they are emitting light in the frequency of their vibration. You remember? Simple harmonic motion. Every vibration has a frequency. So these oscillators will emit light in their vibrations. Max Planck accepted it. Okay, this is correct. A black body radiation was produced by submicroscope, which is not visible to our eyes. Electric oscillators, which he called resonators. Only he gave a name to these oscillators. He said resonators. Planck named submicroscopic electric oscillators as A. Resonators, B. Simple harmonic, simple pendulum, C. Resistor, D. Blah blah. So correct answer is resonator. We have to know this. Second thing, the wall of a glowing cavity. Yani these black bodies wall were composed of billions of these oscillators. Billions of them. All are vibrating at a different frequency. Yeah, like every pendulum has a different frequency depending on their length. Every mass spring system has a different frequency depending on their mass and spring constant. These resonators also have a different frequency, all of them. Max Planck also said the same thing. Okay, this is also correct. I'm saying the same thing. So the walls of the glowing cavity were composed of billions of these resonators, all vibrating at different frequencies. Correct. Yeah, the first and second steps are the same in both classical theory and Max Planck theory. But third step is different. What is the difference? Classical theory says that energy of these resonators were continuous. Continuous. Oscillators can absorb and give off energy at any value. How much energy is given to this black body? They will take that energy and they will give it out. It doesn't matter if it's low or high or middle, it doesn't matter. They take and give. Just like somebody goes to a restaurant, sitting on a table, and eats everything what the waiter brings. You are eating it, he brings meat eating, he brings the chicken eating. You don't choose it. Then you eat it all, and after that you produce energy. This is what classical physics tells. But now here Planck made a big difference. He said that these resonators could only absorb and then emit certain discrete like steps amount of energy. Yeah, like this. Okay, I am sitting on a table. Waiter is bringing me foods. I am looking at the food. Oh, I don't want this. Then waiter bring another food. I will eat this. You are choosing food. Yani resonators are choosing the energy. They don't accept every energy. That's why they cannot give out every energy. So then predict that. Which one produces more energy? The one who eats everything, or the one who eats not everything, some certain things? Of course, everything, there is more energy is produced. If you are starting to choose what you are going to eat, in this case, energy given out by you is going to be small. This is how Planck explained that decrease in the intensity of the light. He said that no, resonators don't take every energy given. They are taking some discrete amount of energy. That's why energy given out at this area, ultraviolet side, is less than here. Yeah, in here they accept more energy, They give it out more energy, but in here they accept less energy, or less number of oscillators accept energy. This one intensity decreases. This was the difference between the Planck's model and classical theory.